This is the last recorded lecture for Set A in Chapter 3. I went back a little bit to a slide that we've already seen, but I just want to review with you the passive transport through the plasma membrane through the phospholipid bilayer. So the first type of passive transport that we discussed was simple diffusion. And this is when molecules move from their high concentration gradient, in this case, in this picture, it's in the extracellular fluid, to their low concentration gradient. And they go directly through the phospholipid bilayer, so they have to be small and lipid soluble. And some examples of substances that diffuse directly through the phospholipid bilayer are gases like oxygen and carbon dioxide, and nonpolar lipid substances like steroid hormones. Okay, and then we looked at facilitated diffusion, which can be carrier-mediated facilitated diffusion, so facilitated diffusion is just like simple diffusion, except that the substance that is diffusing across the plasma membrane is not lipid soluble. So it has to travel either through a channel protein that is continuously open for diffusion. Sometimes we call these leak channels, L-E-A-K, leak channels. And the other way is through a carrier protein. And this is a little bit more complex because the substance has to bind with the carrier protein, and then the carrier protein will change shape and transport the substance across the plasma membrane. So molecules that are going to move across the plasma membrane by facilitated diffusion are going to be, and remember this was incorrect, hydrophilic, water-loving, or water-soluble is probably a better way to say it, water-soluble. So hydrophilic molecules like glucose and other sugars, because sugars are soluble in water, most amino acids, and the majority of amino acids, and ions, which would be like sodium or potassium. Anyway, they would be atoms that have a charge, a positive or negative charge. So these substances can move through a carrier protein or a channel protein, but they're still moving with their concentration gradient from high to low concentration. This image is showing you a carrier that's transporting glucose. Glucose is shaped like a hexagon, so we know this is glucose. The glucose concentration is high in the extracellular fluid, and it is low in the cytosol or cytoplasm inside the cell. So we're still seeing movement from high to low concentration, but this time it is by binding. See how the shape of the glucose fits the binding sites on the carrier protein. Binding chemically with the carrier protein, causing the carrier protein to change shape, releasing the glucose into the area of its low concentration. So that's an example of carrier-mediated. And then channel-mediated facilitated diffusion happens through leak channels or leakage channels, like I mentioned before, which are always open. Or there are some channels that have a gate that open in response to a chemical signal or an electrical signal, a voltage change. One type of channel that's specific to water is called an aquaporin. But these are channels that are just open channels that allow the substance to move. Excuse me. And these are going to be water-soluble substances. They'll either be polar, covalent substances, or they will have a charge, or they will, be ionic, but they move from their high to low concentration through a channel protein. And then we have osmosis, and that is another type of passive transport. It is the diffusion of water across the plasma membrane through, it can be through the lipid bilayer because water is small, but a lot of times it is through aquaporins, which are channel proteins specifically for water. So what happens in osmosis is that water is the molecule we're looking at. So water is moving from where the water concentration or water levels are higher to where the water levels are lower through this aquaporin channel protein that is specifically dealing with water. So we call it osmosis. And to look at how this really happens and how to figure out which direction water is going to move, we don't normally list the concentration of water. That's just not how we do it. When we list a concentration, we list the concentration of the solute. So if the solute molecule, for example, is sugar, if we look at this U tube, it's literally a glass U-shaped tube that has a membrane down at the bottom in the center. And it's got a solution on the right side that has a higher concentration of sugar in it than on the left side. Okay, so if sugar could diffuse, I'm so sorry, I didn't mean to do that, but sugar would move from the right side back to the left side, from its high to its low concentration. But if sugar is too large to diffuse across the membrane, then water is going to move in a direction that will cause the solutions on both sides to reach equilibrium. So the water is actually going to move from the left side to the right side because there's more water, there's a higher concentration of water over here than there is over here. So I always think of it like this: water follows solute. Water goes to the higher solute concentration. And actually, I don't want to re-record this, but I should read before I start speaking. In this case, it says both solute and water molecules move down their concentration gradients. So in this case, the sugar is small enough to pass across. So what we see in this case is that the sugar moves until both sides have equal concentrations of sugar. But if the sugar couldn't pass across, the water would move, and it would move into the right side. It would move toward the higher solute concentration to basically try and dilute it until it reaches equilibrium with the left side. So now we can see a situation like that happen. This is the picture that I should have been showing you. So in this case, the membrane, look at the holes in the membrane. The pores in the membrane are too small for the sugar or solute molecules to pass. So sugar can't move from its high concentration to its low. So what can happen to cause these solutions on either side to reach equilibrium is water can move into the right side. And as it moves into the right side, it dilutes this higher concentration. It used to be higher concentration of sugar, until water will move until both sides reach a kind of an equilibrium or equal concentration of solute. Now, we're going to talk about tonicity. And tonicity is the ability of a solution to change the shape or tone of cells by altering the cell's internal water volume. We look at red blood cells a lot of times in situations with tonicity. So if a red blood cell is placed into an isotonic solution, or the blood plasma is isotonic compared to the fluid inside the red blood cell, then the red blood cell will not change shape. There will not be a net movement of water in or out of the cell, so it won't swell and it won't shrink. It'll stay the same size. But if the red blood cell is placed into a hypertonic solution, and that means that the solution has a higher concentration of solute than inside the cell, so like a really salty solution, a solution with lots of salt in it, what's going to happen is water is going to flow into the higher concentration of solute. So it's going to leave the cell and cause the cell to shrink, and we call that crenation. So if a cell is placed into a hypertonic solution, it will shrink because it loses water. Water moves toward the solution outside the cell, which is more concentrated. And then if a cell is placed into a hypotonic solution, that means the solution outside the cell is more like, distilled water. It's more diluted than the solution inside the cell. So it has much less solute in it, and the water is going to move from outside to inside the cell, and it can lead to cell bursting. It will cause the cell to swell, and it can lead to cell bursting, which we call lysing or cytolysis. C-Y-T-O-L-Y-S-I-S, cytolysis. All right. We have pictures here of what happens to a red blood cell placed in an isotonic solution. It looks nice and round and healthy. It hasn't gained water and it hasn't lost water. If the red blood cell is placed in a hypertonic solution, which is much more concentrated than on the inside of the red blood cell, it's going to lose water and shrink. And if it does that, it's called crenation. And then if it's placed in a hypotonic solution like distilled water, a solution that has a lower concentration of solute than inside the cell, then the water will move into the cell will swell, and it can burst, and this is called cytolysis. This is a really good animation. I encourage you to watch it. It's slide number 69, and that is it for our slideshow.